All right, let's dive right in. Welcome to this explainer where we are going completely under the hood of the Controller Area Network, or CAN bus. I'm really pumped to walk you through this today because we're going to decode the physical layer of the CAN bus so that it just instantly clicks and, more importantly, stays locked in your long-term memory. Look, whether you're a student just figuring this out or a seasoned engineer, truly grasping the bare metal physics of this protocol is an absolute game changer. So, here's our game plan for today. We'll be hitting the pain point, the core concept, the rules of CAN, a real-world transceiver walkthrough, the split termination gotcha, and we'll wrap up with your critical takeaways. Let's get right to it. Section 1, the pain point, extended network failures. Let's talk about that totally relatable frustration we've all faced when the hardware just flat out refuses to cooperate. Picture this. You've spent weeks writing flawlessly optimized C++ code for your CAN controllers. Everything runs perfectly on your test bench. But the very second you deploy this system into a real vehicle or, say, an industrial plant with a 50-meter cable run, the network suddenly starts dropping packets. It just fails entirely. So why does that happen? Well, the answer actually isn't in your software. You literally cannot code your way out of a physical layer problem. To fix this, we have to look at the exact physics of how those bits travel down the copper wires. And that brings us to Section 2, the core concept, dominant versus recessive states. This is the absolute foundational theory of how signals move on a CAN bus. Now, to make sure you never forget this, I want you to use this visual analogy. In the CAN protocol, a logical 1 is called the recessive state, and a logical 0 is the dominant state. Think of the recessive state like a perfectly quiet room. In this quiet room, anyone can step up and gently speak. But the dominant state, that logical 0, is like someone stepping into that room and shouting through a massive megaphone. If someone is speaking quietly and someone else blasts a megaphone at the exact same time, the megaphone instantly and completely overpowers the quiet voice. The quiet room is physically overwritten. And you know what? That is exactly how CAN bus arbitration works. If node A transmits a recessive 1 and node B transmits a dominant 0, that dominant 0 physically crushes the 1 on the wire. The 0 always wins. Moving on to Section 3, the math and the rules of CAN. Let's take a look at the rigorous electrical standards that actually dictate this dominant and recessive behavior. Notice how the math physically represents that megaphone analogy we just talked about? Let's look at the high-speed CAN spec first. Check out the voltage levels. During a recessive state, a logical 1, both the CAN high and CAN low wires just sit there resting at 2.5 volts. That means the differential voltage, delta U, is exactly 0 volts. There's your quiet room. But to transmit a dominant logical 0, CAN high is actively driven up to 3.5 volts and CAN low is pulled down to 1.5 volts. This creates a powerful 2-volt differential. That 2-volt gap, that is the megaphone. Now contrast this directly with the low-speed CAN specification. It's a totally different beast. For low speed, a recessive state actually sits at a negative 5-volt differential, with CAN low up at 5 volts and CAN high at 0. A dominant state shifts this to a positive 2-volt differential. You absolutely cannot mix these two standards on the same physical bus. Their electrical realities are just completely incompatible. And this brilliantly illustrates a really strict physical trade-off in network design. There's a rigid inverse relationship between your data rate and your maximum cable length. If you want to push data at a blistering 1,000 kilobits per second, your physical bus cannot exceed 46 meters, period. But if you need to span a massive 1,300-meter industrial facility, you're forced to drop your speed all the way down to 50 kilobits per second. You might be wondering why? Well, it's because of arbitration. When multiple nodes start talking at once, the physical voltage changes actually need time to travel down the entire length of the copper wire and bounce back so every single node can hear the megaphone. If your data rate is too fast on a cable that is too long, the bit time will end before the signal physically reaches the other side and the entire network crashes. You just can't cheat physics. Let's jump to Section 4, real-world walkthrough example. We're going to apply the math we just learned directly to the silicon. Let's methodically walk through the internal structure of a CAN transceiver. When the CAN controller wants to send a dominant 0, it sends a low signal to the TXD pin. This actively switches on transistor T1 and transistor T2. Watch what happens here. Transistor T1 physically connects the CAN high line to VCC, the power source, pulling it up. At the exact same time, transistor T2 connects the CAN low line to ground, pulling it down. These two transistors acting together are exactly what forcefully injects that 2-volt differential onto the bus. But when the controller wants to send a recessive one, it simply turns both transistors off. It completely stops driving the bus, and the lines are left to float back to an equal voltage. Which naturally leads us into Section 5, the split termination gotcha. This right here is the physical layer pitfall that ruins countless engineering projects. Think about it. If you turn off transistors T1 and T2, how do the CAN high and CAN low lines actually get back to their 2.5-volt resting state? They need a path for the electrical potential to equalize. This is exactly why termination resistors at both ends of your CAN bus are absolutely mandatory. Now, a highly robust real-world solution for this is called split termination. Instead of just slapping a single 120-ohm resistor across the lines, engineers use two 60-ohm resistors in series, and right at the middle point between them, they connect a 4.7 nanofarad capacitor that goes straight to ground. This is brilliant because it doesn't just equal out the voltage. That capacitor acts as a low-pass filter, draining high-frequency electromagnetic interference right out of your network. So the underlying physics summarize the crucial point perfectly. Without active termination, the recessive state relies entirely on internal 25 kilo-ohm resistors, taking too long to return the differential to zero and destroying bus logic. You see, inside every single transceiver, there are weak 25 kilo-ohm resistors. If you forget to put your 120-ohm terminators on the physical ends of your cables, those internal 25K resistors become the only way for that 2-volt dominant signal to drain away. Because 25,000 ohms is such a massive resistance, it acts like a tiny clogged drain pipe. The voltage differential bleeds off so slowly that by the time the next bit is supposed to be read, the bus is still carrying the ghost of the previous dominant zero. The result? You get constant read errors, and your network completely fails. All right, let's wrap this up in Section 6, Critical Takeaways and Outro. Time to really lock in what we've learned. Here is your rapid-fire recap. Number 1. A dominant logical 0 physically overrides a recessive logical 1. Always remember the megaphone in a quiet room. Number 2, you cannot cheat physics. Higher data rates strictly limit your maximum cable length because the signal literally needs time to physically propagate for arbitration. And number 3, proper termination, ideally split termination with two 60-ohm resistors and a capacitor, is absolutely non-negotiable. Without it, the voltage simply cannot equalize fast enough and your network is gonna crumble. I really hope this explainer has completely demystified the physical layer of the CAN bus for you. The next time you're staring at a dropped packet error on a massive cable run, you're going to know exactly what's happening down at the silicon and voltage level. But hey, we're just scratching the surface of hardware mastery here. If you want to keep leveling up your engineering skills, make sure you subscribe to the Spectrum Speak channel right now for more EMC and Automotive Communication Protocol survival guides. So before your next deployment, ask yourself, are you just trusting your code, or are you actually respecting the physics of the wire? Keep building, keep troubleshooting, and I'll catch you in the next one.